In the deepest silences between the galaxies, where the light of one island universe fades before another's begins, there is an emptiness so profound it defies human comprehension. This void, cold and impossibly vast, seems to be the default state of existence. It is the canvas upon which the brilliant, chaotic tapestry of creation is thinly painted. We have long looked into this profound dark and believed it to be precisely that, nothing. A chasm of non-existence separating the glittering cities of stars. But this perception, like so many of our cosmic assumptions, is a profound illusion. The truth is far stranger and infinitely more violent. That seemingly barren space is haunted. It is the scene of the largest, most audacious heist in the history of the cosmos. A crime perpetrated on a scale so grand it has shaped the very structure of reality. The stolen goods, half of everything that was ever meant to be. Half of all the ordinary matter, the stuff of stars, of planets, of life itself. It has vanished from sight, spirited away from its galactic birthplaces. For decades, astronomers looked at their cosmic ledgers and saw a terrifying discrepancy. Their calculations based on the pristine echoes of the Big Bang told them exactly how much material the universe should contain. Yet when they counted up all the luminous stars, all the swirling nebulae, and all the familiar dust, they found only a fraction of the expected total. The universe we could see was a shadow of the universe that ought to exist. The search for this phantom mass became one of the most urgent quests in modern science. It was a hunt for a ghost, a search for the very soul of the cosmos. And the trail of evidence would not lead to some subtle, unknown law of physics. It would lead back to the most ferocious monsters the universe has ever conceived. It would point to the ravenous, light-devouring hearts of galaxies themselves, to the supermassive black holes that in the universe's wild youth didn't just consume what fell into their grasp. They unleashed forces so cataclysmic, so astonishingly powerful, that they blasted the cosmos apart. They are the reason the void is not empty. They are the architects of the universe's magnificent and terrifying desolation. To understand the scale of this cosmic larceny, we must first journey back to the beginning, not just to the dawn of stars, but to the very first moments of existence. In the searing, incandescent aftermath of the Big Bang, the universe was a homogeneous soup of energy and elementary particles. As it expanded and cooled, this primordial plasma underwent a miraculous transformation. Within the first few minutes, the fundamental forces of nature orchestrated the creation of the first atomic nuclei. This process, known as Big Bang nucleosynthesis, forged the universe's elemental building blocks. Vast quantities of hydrogen, a considerable amount of helium, and trace amounts of lithium. This is what physicists call baryonic matter, the ordinary stuff from which you and I are made. The cosmic recipe was set, the ingredients precisely measured in that initial cosmic kitchen, and we have an exquisitely detailed photograph of this nascent universe. It is the cosmic microwave background, the faint, persistent afterglow of creation's first fire. Imprinted upon this ancient light is a blueprint of the cosmos at just 3,800,000 years of age. It reveals with breathtaking precision the exact proportions of the universe's contents. Imagine you are given the original, infallible architectural plans for a grand celestial city. These blueprints detail every single brick, every stone, every ounce of material required for its construction. The cosmic microwave background is that perfect primordial blueprint. It tells us that for every measure of the familiar baryonic material, there should be about 5 measures of an unseen, mysterious substance we call dark matter. But it also gives us a hard number, a non-negotiable budget for the normal stuff. For decades, astronomers set about the laborious task of taking inventory of the modern universe. They used powerful telescopes, to count the galaxies, to measure their starlight, to weigh their clouds of gas and dust. They were conducting a cosmic census, expecting their final tally to match the primordial blueprint. But a disturbing, bewildering pattern began to emerge. The numbers were catastrophically wrong. The grand celestial city was only half built. Star by star, galaxy by galaxy, the census came up short. When they added up everything they could see or detect directly, all the suns, all the planets, all the interstellar clouds, it accounted for only about half of the baryonic matter predicted by the pristine physics of the early universe. This wasn't a minor rounding error. It was as if half of North America had simply vanished from the globe. This enigma became known as the missing baryon problem. It was a profound crisis in cosmology. Physics is built upon conservation laws. Things don't just disappear. Where had it all gone? Where was the other half of everything? The initial suspects were mundane. Perhaps it was hiding in faint, dim stars that we couldn't easily see. Or maybe it was locked away in cold, dark clumps of gas that emitted no light. Scientists searched fruitlessly for these hidden reservoirs within galaxies. They scanned the galactic halos, the sparse outer regions of stellar systems for any sign, but every search turned up empty. The missing material was not merely hiding in the shadows of galaxies, it seemed to be gone from them entirely. The implication was as unavoidable as it was shocking. Something had to have physically removed it. Something had scoured the galaxies clean, ejecting trillions of solar masses of gas into an unknown realm. The hunt was on for a culprit with sufficient power, an engine of almost unimaginable violence. And in the very heart of every major galaxy, including our own Milky Way, such a suspect lurked. A creature of pure gravity, an object so dense that it tears the fabric of space-time itself. The supermassive black hole. The concept of a black hole is not new. It is an idea that has haunted scientific thought for centuries. In the late 18th century, the English natural philosopher John Michell and later the French polymath Pierre-Simon Laplace independently conceived of dark stars. They reasoned using Newtonian physics that an object could be so massive and compact that its escape velocity would exceed the speed of light. Light itself, they theorized, could not escape its gravitational pull, rendering the star invisible. It was a stunning piece of intuition, an idea far ahead of its time. But it would take Albert Einstein's revolutionary theory of general relativity in 1915 to give this notion its modern, terrifying form. Einstein revealed that gravity is not a force but a curvature in the geometry of space-time caused by mass and energy. A few months later, the German physicist Karl Schwarzschild, while serving on the Russian front in World War I, found the first exact solution to Einstein's equations. His mathematics described a point of infinite density, a singularity where the laws of physics break down, surrounded by a one-way membrane, the event horizon. Anything that crosses this boundary, including light, can never escape. The black hole was born into physics. For decades, these objects were considered mathematical curiosities, but astronomical evidence began to mount for the existence of stellar mass black holes, the collapsed corpses of giant stars. Then came a discovery of a different order of being altogether. Astronomers studying the motions of stars at the centers of galaxies noticed something profoundly strange. Stars were orbiting a central point at incredible speeds, whipping around something that was completely invisible yet possessed the gravitational influence of millions or even billions of suns. These were the supermassive black holes, monstrous titans compared to their stellar cousins. How they came to be is still a subject of intense debate. Did they form from the collapse of the universe's very first gargantuan stars, or did they grow from smaller seeds relentlessly merging and feeding over cosmic eons? Whatever their origin, they settled into the gravitational heart of nearly every galaxy, becoming the silent, sleeping anchors around which trillions of stars would spin for eternity. But these beasts are not always asleep. In the early chaotic eons of the universe, galaxies were rich with gas, the raw fuel for star formation. This abundant material would spiral inward towards the galactic center, drawn by the irresistible gravity of the central behemoth. As this matter fell, it didn't plunge directly in. Instead, it formed a vast, flattened, rotating structure called an accretion disk. To visualize this process, do not think of a simple drain. Instead, imagine a cosmic grinding wheel, 1,000,000 times wider than our solar system. Gas and dust, torn apart stars and interstellar clouds are all dragged onto its surface. As this material swirls inward at near light speed, friction and magnetic turbulence heat it to unimaginable temperatures. The accretion disk begins to glow with a ferocity that can outshine the combined light of all the billions of stars in its host galaxy. This blazingly luminous object is a quasar. It is the visible tantrum of a feeding supermassive black hole, first detected as mysterious point-like radio sources in the 1,950 seconds. Their true nature baffled scientists. In 1963, the astronomer Martin Schmidt analyzed the light from one of these objects, 3C 273. He found its spectral lines were shifted so dramatically toward the red end of the spectrum that it had to be billions of light years away. For it to be visible from such a staggering distance, it had to be radiating more energy than 100 Milky Ways combined. This was no star. It was a new, terrifyingly powerful class of cosmic engine, and this engine is the weapon that committed the great cosmic robbery. The sheer brightness of the quasar exerts an outward pressure, a wind of pure light that can push gas away. But this is only part of the story. The most destructive force comes from the complex physics of the spinning disk itself. The accretion disk becomes a cosmic dynamo, generating magnetic fields of breathtaking power. These magnetic field lines, anchored in the swirling plasma, get twisted up like colossal rubber bands. Eventually, this stored magnetic energy unleashes, launching twin jets of superheated particles from the poles of the black hole. These jets are fired into space at velocities approaching the speed of light. They are focused beams of destruction, cosmic blowtorches that can extend for hundreds of thousands of light years, far beyond the confines of the host galaxy. This entire outflow, the combination of radiative pressure and the powerful jets, creates a phenomenon known as galactic feedback. It is the supermassive black hole pushing back against the very galaxy that feeds it. This feedback is the mechanism of the heist. In the young universe, galaxies were small, compact, and brimming with the primordial hydrogen and helium gas from the Big Bang. This was the inheritance of the cosmos, the raw material for generations of star formation. When the central supermassive black holes ignited as quasars, they unleashed their cataclysmic winds and jets directly into this rich gaseous environment. The effect was not subtle. It was a galactic-scale explosion, a cosmic shockwave that ripped through the nascent galaxy. Picture a fledgling island nation just beginning to build its first cities from its abundant natural forests. Suddenly, the volcano at the island's center erupts with a force so titanic it doesn't just destroy the cities. It blasts the forests, the soil, the very bedrock of the island into the surrounding ocean, scattering it for thousands of miles. The island is left scoured, barren, a fraction of its former potential, while its lost substance is dispersed and diluted into the vast empty sea. This is what the quasars did to their host galaxies. They acted as cosmic snowplows, driving the majority of the galaxy's gas reserves out into the void. This material was not swallowed by the black hole, nor was it annihilated. it was simply expelled, banished from its home. The jets and winds accelerated this gas to incredible speeds and heated it to millions of degrees, creating a tenuous, searingly hot plasma. This superheated, ejected material then expanded into the great voids of intergalactic space. It was spread so thin and heated to such extreme temperatures that it became effectively invisible. It was too hot to form atoms that could be detected by radio telescopes like cold gas clouds, and it was far too diffuse to coalesce and shine like a star. This is the hiding place of the missing baryons. They are not missing at all. They reside in a vast ethereal ocean of superheated plasma that fills the space between galaxies. This realm is now known as the Warm-Hot Intergalactic Medium, or the WHIM. The theory was elegant and powerful. It explained not only the missing matter, but also another cosmic puzzle: why the largest galaxies seem to stop forming stars. The supermassive black hole acts as a galactic thermostat. If a galaxy accumulates too much cold gas, it fuels the central black hole, which ignites as a quasar. The quasar then blows the gas away, starving the galaxy of fuel and shutting down star formation. This self-regulating cycle, this dance of gravity and destruction, sculpts the evolution of galaxies across cosmic time. But proposing a theory is one thing, finding the proof is another. How could scientists possibly detect a substance so diaphanous and so vast? Searching for the WHIM directly was like trying to find a specific wisp of steam in a planet-sized fog bank. The breakthrough came not from trying to see the material itself, but by observing its shadow. The solution required using the universe's most distant lighthouses, other quasars. Imagine a powerful searchlight on a distant coast, shining its beam toward you across a foggy bay. You cannot see the individual water droplets of the fog, but as the light passes through, the fog scatters and absorbs some of it, dimming and coloring the beam. By analyzing the precise character of the light that reaches you, you can deduce the properties of the fog it traversed. Astronomers used this exact principle on a cosmic scale. They identified extremely distant quasars, objects from the very early universe, whose light has been traveling for billions of years to reach Earth. This ancient light serves as the searchlight beam. On its long journey, this beam must pass through the immense stretches of intergalactic space, the very regions where the WHIM is thought to reside. If the WHIM is real, this superheated plasma, though nearly invisible, should leave a telltale fingerprint on the quasar light passing through it. The fingerprint would take the form of absorption lines. The searingly hot temperatures in the WHIM strip electrons from atoms. An oxygen atom, for example, might be stripped of 6 or 7 of its 8 electrons. This highly ionized oxygen has a unique property: it absorbs X-rays of a very specific energy. So, if a beam of X-rays from a distant quasar passes through a cloud of the WHIM, those specific X-ray energies will be absorbed by the oxygen ion. When astronomers analyze the spectrum of that quasar light, they should see a dark line, a tiny sliver of missing light at exactly that energy. Finding that specific absorption line would be like finding a DNA sample of the missing matter. This was a monumental observational challenge. The effect was predicted to be incredibly subtle, requiring space-based X-ray observatories of immense sensitivity, like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton. For years, teams of scientists pointed these sophisticated instruments at distant quasars, collecting precious photons one by one. They painstakingly analyzed the X-ray spectra, searching for the ghostly imprints of the WHIM. The early results were tentative, tantalizing, but inconclusive. Then, a breakthrough. By combining observations from multiple telescopes and aiming them along sightlines that passed through known filaments of the cosmic web, the great tendrils of galaxies and dark matter that connect the universe, the signature began to appear. Faint but distinct absorption lines emerged from the noise. The fingerprints were there exactly where the theory predicted they would be. The highly ionized oxygen, a clear tracer of million-degree gas, was lurking in the cosmic voids. Subsequent studies confirmed the finding again and again. By mapping these absorption lines across the sky, astronomers were finally able to account for the missing baryons. They were exactly where the models of galactic feedback said they would be not gone, but banished. The case was closed. The supermassive black holes were the culprits. Their ancient, violent outbursts had fundamentally re-engineered the cosmos, populating the emptiness with the ghost of what might have been. This discovery reshapes our entire understanding of the universe and our place within it. It carries a profound and somewhat melancholy philosophical weight. It means that every galaxy, including our own, is a pale imitation of its potential self. Half of the raw material that could have formed new stars, new solar systems, and perhaps new arenas for life to emerge was violently cast out into a sterile, unusable void. The universe is dimmer, emptier, and more sparsely populated with stars than it was destined to be. We are living in the quiet aftermath of a cosmic sterilization event. The evidence of this violent past is even etched into our own galactic home. The supermassive black hole at the center of the Milky Way Sagittarius A star is currently a sleeping giant. It is a quiescent, starved behemoth consuming only a few meager wisps of gas. But it was not always so peaceful. In 2010, astronomers using the Fermi Gamma Ray Space Telescope discovered two colossal structures extending above and below the plane of our galaxy. These structures, now called the Fermi bubbles, are enormous lobes of superheated gas emitting high-energy gamma rays. They stretch for 25000 light-years in each direction, a ghost of a past eruption. A few million years ago, a relatively recent event, in cosmic terms, our galaxy's central black hole must have feasted on a large cloud of gas or an unfortunate star. It flared up, launching a powerful blast that inflated these gargantuan bubbles. We are living within the blast zone of our own black hole's recent fury. This revelation forces us to see the cosmos not as a static, majestic cathedral, but as a dynamic, evolving ecosystem shaped by a constant battle between creation and destruction. Gravity, the force of accumulation, relentlessly pulls matter together to build galaxies and stars. But the feedback from the supermassive black holes it creates provides the opposing force of expulsion. This cosmic tension dictates the fate of galaxies, determining their size, their shape, and their ability to foster life. What is the ultimate fate of this exiled matter, this lost half of the universe? Will it remain forever adrift in the intergalactic medium, slowly thinning out as the relentless expansion of space driven by dark energy pulls everything apart? For the most part, this seems to be its destiny, a vast, silent, and permanent memorial to the power of the quasars. Some of it, over unimaginable timescales of trillions of years, might slowly cool and rain back down onto the filaments of the cosmic web. It could one day be drawn back into the gravitational embrace of a galaxy, offering the fuel for a final sputtering generation of stars in a cold and dying universe. But for now, and for all of human history to come, it will remain out there. When we gaze up at the night sky, at the dark lanes between the stars and the immense gulfs separating the faint smudges of distant galaxies, we are not looking at nothing. We are looking at the universe's great diaspora. We are peering into a cosmic wilderness populated by the displaced atoms that were denied a chance to become part of a sun, a world, or a living creature. the great mystery of the missing baryons is solved. But its solution leaves us with a more profound sense of the universe's awesome and terrifying power. The same engines of gravity that hold our galaxy together were once responsible for tearing it and every other galaxy apart. We exist in a delicate balance in the quiet interludes between titanic outbursts. Our existence is a consequence of what was left behind. We are the survivors of a cosmic storm built from the fortunate matter that managed to cling to its galactic home while half the cosmos was blown away. The darkness is not empty, it is full of ghosts,